Hello students, today we will discuss about roles and Lagrange mean value theorem. So at first I will state the famous roles theorem. Okay, let a function f from the closed interval a comma b to the set of all real numbers r such that one f is continuous f is continuous on the closed interval a comma b. Okay, number 2 is f is differentiable on the open interval a comma b, and the number 3 is the image of a and image of b are same. Okay, then f is a function which is satisfying the three conditions. Okay, 1 2 3. Then there exists at least one point okay, C in the open interval a comma b, that is a is less than c and c is less than b. Okay, such that f dash c that means if the derivative of f at the point c is equal to 0. Okay, that means the Rolle's theorem says that if f satisfies these three conditions, then the derivative function of f has at least one root. Okay, so suppose this is our x-axis, this is our y-axis. Okay, now this is our closed interval a comma b. Okay, we have defined one function f which is this. Okay, f is continuous on a comma b, f is differentiable on open interval a comma b, and f a equal to f b. That means we have to join this curve. Okay, so I am erasing this. We have to join this curve. So Suppose this is our curve. Okay, no, not really that. That means fa, that means the height of fa and fb are same. Okay, so if we start the graph of f at this, then that means the height, so this height are same. Okay, okay, fine. So this is not a joining. Okay, this is not a joining. Okay, fine. So Rolle's theorem says that the derivative function of f has at least one 0 in this interval. Okay, so 0 means function, if a function is cutting, then cutting the x-axis, then the point of intersection is called the 0 of the function. Okay, so the function, so Rolle's theorem says that the derivative function of f is cutting the x-axis at least one time. Okay, so this is the main statement of the Rolle theorem. Okay, now this has a proof, but the proof is not in the syllabus, so I have to omit the proof. Okay, now there is another version of a Rolle's theorem for polynomial function. Okay, you know that a polynomial function is already a continuous function. Okay, always continuous. So that means to define Rolle, so to apply the Rolle's theorem, we need a continuous function on a certain interval and differential function on that open interval. Okay, and fa equal to fb. So polynomial is one kind of function which is continuous on any interval, which is differentiable also, and which has 2, 3 or many points which have same images. Okay, so I am writing this. Okay, so Rolle's theorem for polynomial. Rolle's theorem for polynomial. If a polynomial px has at least two roots, okay, then between any two real roots, there exists at least one real root, one real root of the derivative function f dash, okay, or derivative polynomial. Then there exists at least one real root of the derivative function f dash, okay. So Rolle's theorem assured that if px is a polynomial, if px is a polynomial, px having two real roots, then having at least two real roots, then the derivative polynomial px, has at least one root in between that two real roots of fx, okay. So that means two real roots of px is separated by at least one root of p dash x, okay. So this is the main thing of Rolle's theorem. Okay, so now I will write the Lagrange mean value theorem, okay. So I am clearing my canvas. Mean value theorem, which is proved by Lagrange. Mean value theorem. So what Lagrange mean value theorem says, that let f be a function from the closed interval a comma b to real number r, okay, be such that one, f is continuous and f is continuous on the closed interval a comma b, okay. Condition 2 is f is differentiable, on the open interval a comma b, okay. Then there exists at least one point, C in a comma b open interval, okay, such that f of b minus f of a by b minus a is equal to f dash c. Okay, so it is quite similar to Rolle's theorem, but it is more greater, okay, than Rolle's theorem, because if we apply the condition, especially if b is equal to f a, then we will get from this expression f dash c is equal to 0. Okay, so if we apply this, then this will then whole theorem is converted to a Rolle's theorem. Okay, but if we take fb not equal to fa, then there exists always a c in this interval a comma b open interval, such that fb minus fa by b minus a is equal to f dash c. Okay. So what is meant by this quantity? Okay, now I am drawing the picture of this theorem. Okay, so at first I am drawing the picture of Rolle's theorem. Okay, so suppose that this is our x-axis. Okay, so this is our a, this is our b. Now in Rolle's theorem we have the same height of AB, right? So FA and FB, that means FA and FA equal to FB means the height of this straight line are same. Okay, now this is the curve, this is the curve which is fx. Okay, this is interval, so for each point on this line we will get a point on xy plane. Okay, and to joining them we will get a curve. Okay, so by Rolle's theorem, this is by Rolle's theorem we will get at least one c in between a and b, such that f dash c is equal to 0. So f dash c is actually the tangent, the slope of the tangent, okay, at the point this. Okay, so this point is fc. So this is c, so this is the point c comma fc, c comma fc. So this is the gradient, so this is the tangent which is parallel to x-axis. Okay, which is parallel to x-axis. So always we get so by Rolle's theorem we can assert that always we will get always a tangent of a curve which is parallel to x-axis. Okay, and as I said that the Lagrange mean value theorem is generalized version of Rolle's theorem. So mean value theorem says that this is A and this is B and this is our curve. So here FA is not equal to FB. So this is our curve, and Rolle's theorem and Lagrange mean value theorem says that we can always this is our C, okay, this is our C. So this theorem says that we can always draw a tangent at the point C comma FC, okay, on the curve fx. So this is the significance of Lagrange mean value theorem and Rolle's theorem. They are very strong theorem in calculus, okay. So now by this Lagrange mean value theorem we will prove useful result, okay. So I am filling my canvas. Okay. One small application which is called a theorem or problem, whatever you can say. Let a function f from closed interval a to b to r be continuous, okay, be conti and differentiable on open interval a comma b, okay. So if dash x is equal to 0 for all x belongs to the closed interval a comma b, okay. No, this is not a this is not a closed interval, this will be open interval, okay, because we have said that differentiable on the closed open interval a comma b, so we cannot take the point a and b endpoints, okay. Then f is a constant, function on a comma b, okay. So this is the problem. So if we prove that, then we have to apply just the Lagrange mean value theorem, okay. So what is constant function? Constant function means that if fx is equal to c for all x belongs to a comma b, then f is called constant function, okay. Then f is called constant function, where c is a constant, right? C is a constant, okay. So let x1 and x2 belongs to the closed interval a comma b, okay, and a less or equals to x1 less or equals to x2 less or equals to b, fine. Then f is continuous on, then f is continuous on the closed interval x1 comma x2, right? Okay, the equality between x1 and x2 doesn't hold. Okay, so f is continuous on x1 comma x2 closed interval and differentiable on the open interval x1 comma x2. Okay, then we can apply the Lagrange mean value theorem. So by LMVT means Lagrange mean value theorem. By LMVT, there exists xi in between a comma b such that f dash xi is equal to f of x2 minus f of x1 by x2 minus x1, right? Okay. But by the hypothesis, but by the hypothesis means which is already given to you to prove the theorem. Okay, so by the hypothesis, here hypothesis is f be a continuous function differentiable on a comma b and f dash x equal to 0 for all x belongs to a b. So this is the but by the hypothesis f dash xi, because for all x belongs to a comma b, f dash x equal to 0, so xi is one of the x from a comma b. Okay, so f dash xi is equal to 0. Okay, and it means f of x2 is equal to f of x1. That means if a fraction, this is a fraction. Okay, this is a fraction. So if a fraction is equal to 0, that means the numerator is 0. Okay, that means if this fraction is 0, that means fx2 minus fx1 is equal to 0, so fx2 equal to fx1. So since x1 and x2 are arbitrary, so since x1 and x2 are arbitrary, so fx is equal to fy for any xy from the closed interval a comma b. Okay, so that means the image of each point in a comma b closed interval are actually same. So that means fx is equal to actually a constant k. K is a real constant. Okay, so which proves that the function is constant function on a comma b closed interval. So such a powerful theorem is made by Lagrange, okay, which is fantastic actually. Okay, so there is another application of Lagrange mean value theorem, which is okay. At first, I have to define one thing, that if f is a function from an interval to r, okay, then if for each x1 x2 belongs to I, such that, not such that, with x1 is less or equals to x2, that means x1 is either equals to x2 or less than x2, then okay, no, not then, such that then if for each x1 x2 for belongs to I with x1 less or equals to x2, such that f of x1 less or equals to f of x2, then f is called monotone increasing function, okay, on I, okay, and if for each x1 x2 from I with x1 less or equals to x2, such that f of x1 is greater or equal to f of x2, then f is called monotone decreasing, okay, f is called monotone decreasing on I. So this is very easy to show that if we draw the picture, then suppose this is our interval AB, okay, this is our interval AB. If a function, so here a is small b is greater, this. So if we draw a function that, then each fxy, that means this is our y-axis, okay. Now these are the points. Now one arbitrary point on the line is x comma fx, okay, and where fx is actually the point on the y-axis, okay. So 0 comma fx. So you can easily see that each fx for each x1 x2 in a comma b, fx1 less or equals to fx2 is maintained in this curve. So this function, whatever it is, if this function is this is a graph of strictly a monotone increasing function, okay. And if we draw the picture AB, which is is this, then this is clearly a picture of a monotone decreasing function. Okay, so by Lagrange mean value theorem we can prove that one useful theory in calculus. So theorem let f from a comma b to r be a continuous function on the closed interval a comma b, and if dash x greater or equal to 0 for all x belongs to the open interval a comma b. Okay, then f is monotone increasing on the interval a comma b. Okay, so similarly we can assume that by the previous theorem, let x1 x2 from the closed interval a comma b with this. Okay, so by LMVT there exists a xi in a comma b open interval such that f of x2 x2 minus f of x1 by x2 minus x1 is equal to actually f dash I, or by the hypothesis if dash x greater or equal to 0 for all x belongs to a comma b open interval, so f dash I greater or equal to 0. That means f of x2 minus f of x1, because x2 minus x1 x2 is always greater than x1. Okay, so this quantity is positive, so that means the sign of this fraction is entirely dependent on this numerator, and which gives us that fx2 minus fx1 greater or equal to 0, which means fx2 greater or equal to fx1. Okay, and since x1 x2 are arbitrary, so f of x greater or equal to f of y for each xy in the closed interval a comma b. So f is monotone increasing. Okay, and the same thing if we replace this this condition by less than or equal to 0, then then this increasing is converted to decreasing. Okay, decreasing. So here the signs are changed. So this that, and so okay, so this lesser equals to 0, so this. Okay, so here only the inequality is and decreasing. Okay, so this is the significance of Lagrange-Mendel theorem. Okay, so Roche theorem is a particular case of Lagrange-Mendel theorem actually. Okay, so this is all about the theorems and their applications. Okay, so I am stopping my class here.